Digital audio broadcasting is a digital radio technology for broadcasting radio stations, used in several countries across Europe and Asia-Pacific. The DAB standard was initiated as a European research project in the 1980s. The Norwegian Broadcasting Corporation launched the first DAB channel in the world on the 1st of June 1995, and the BBC and Swedish Radio launched the first DAB digital radio broadcasts in September 1995. DAB receivers have been available in many countries since the end of the 1990s. DAB may offer more radio programs over a specific spectrum than analog FM radio. DAB is more robust with regard to noise and multipath fading for mobile listening, since DAB reception quality first degrades rapidly when the signal strength falls below a critical threshold, whereas FM reception quality degrades slowly with the decreasing signal. Audio quality varies depending on the bitrate used and audio material. Most stations use a bitrate of 128 kbit per second or less, with the MP2 audio codec, which requires 160 kbit per second to achieve perceived FM quality. 128 kbit per second gives better dynamic range, a signal-to-noise ratio than FM radio, but a more smeared stereo image, and an upper cutoff frequency of 14 kHz, corresponding to 15 kHz of FM radio. However, CD sound quality with MP2 is possible with 256.192 kilobits per second. An upgraded version of the system was released in February 2007, which is called DAB+. DAB is not forward compatible with DAB+, which means that DAB-only receivers are not able to receive DAB+ broadcasts. However, broadcasters can mix DAB and DAB+ programs inside the same transmission and so make a progressive transition to DAB+. DAB+ is approximately twice as efficient as DAB due to the adoption of the AAC+ audio codec, and DAB+ can provide high-quality audio with bit rates as low as 64 kbit per second. Reception quality is also more robust on DAB+ than on DAB due to the addition of Reed-Solomon error correction coding. In spectrum management, the bands that are allocated for public DAB services are abbreviated with TDAB, where the T stands for terrestrial. More than 30 countries provide DAB transmissions, and several countries, such as Norway, Australia, Italy, Malta, Switzerland, the Netherlands and Germany, are transmitting DAB+ stations. See countries using DAB, DMB. In many countries it is expected that DAB will gradually replace FM radio. Norway was the first country to announce national FM radio switch-off starting from 2017. History. DAB has been under development since 1981 at the Institute for Rundfunktechnik. In 1985 the first DAB demonstrations were held at the WARC Orb in Geneva, and in 1988 the first DAB transmissions were made in Germany. Later DAB was developed as a research project for the European Union, which started in 1987 on initiative by a consortium formed in 1986. The MPEG-1 Audio Layer 2 codec was created as part of the EU 147 project. DAB was the first standard based on orthogonal frequency division multiplexing modulation technique, which since then has become one of the most popular transmission schemes for modern wideband digital communication systems. A choice of audio codec, modulation and error correction coding schemes and first trial broadcasts were made in 1990. Public demonstrations were made in 1993 in the United Kingdom. The protocol specification was finalized in 1993 and adopted by the ITUR standardization body in 1994, the European Community in 1995 and by ETI in 1997. Pilot broadcasts were launched in several countries in 1995. The UK was the first country to receive a wide range of radio stations via DAB. Commercial DAB receivers began to be sold in 1999, and over 50 commercial and BBC services were available in London by 2001. The standard was coordinated by the European DAB Forum, formed in 1995 and reconstituted to the World DAB Forum in 1997, which represents more than 30 countries. In 2006, the World DAB Forum became the World DMB Forum, which now presides over both the DAB and DMB standard. In October 2005, the World DMB Forum instructed its technical committee to carry out the work needed to adopt the AAC Plus audio codec and stronger error correction coding. This work led to the launch of the new DAB Plus system. By 2006, 500 million people worldwide were in the coverage area of DAB broadcasts, although by this time sales had only taken off in the United Kingdom and Denmark. In 2006, there were approximately 1,000 DAB stations in operation worldwide. Technology, bands and modes. DAB uses a wide bandwidth broadcast technology, and typically spectra have been allocated for it in band 3 and L-band, although the scheme allows for operation almost anywhere above 30 MHz. The U.S. military has reserved L-band in the USA, only blocking its use for other purposes in America, and the United States has reached an agreement with Canada to restrict L-band DAB to terrestrial broadcast to avoid interference. DAB has a number of country-specific transmission modes. For worldwide operation, a receiver must support all four modes: Mode I for Band 3, Earth; Mode 2 for L-band, Earth and Satellite; Mode 3 for frequencies below 3 GHz, Earth and Satellite; Mode IV for L-band, Earth and Satellite. Protocol stack. From an OSI model protocol stack viewpoint, the technologies used on DAB inhabit the following layers. The audio codec inhabits the presentation layer. Below that is the data link layer, in charge of statistical time division, multiplexing and frame synchronization. Finally, the physical layer contains the error correction, coding, Ofdm modulation, and dealing with the over-the-air transmission and reception of data. Some aspects of these are described below. Audio codec. The older version of DAB that is being used in Denmark *, Ireland *, Norway *, Switzerland * and the UK uses the MPEG-1 audio layer 2 audio codec, which is also known as MP2 due to computer files using those characters for the file extension. Denmark, Ireland, Norway, and Switzerland also use DAB+. The new DAB+ standard has adopted the AAC version 2 audio codec, commonly known as AAC Plus or AAC Pluses. AAC Plus is approximately 3 times more efficient than MP2, which means that broadcasters using DAB+ will be able to provide far higher audio quality of far more stations than they can on DAB, or, as is most likely, a combination of both. Higher audio quality and more stations will be provided. One of the most important decisions regarding the design of a digital radio system is the choice of which audio codec to use, because the efficiency of the audio codec determines how many radio stations can be carried on a multiplex at a given level of audio quality. The capacity of a DAB multiplex is fixed, so the more efficient the audio codec is, the more stations can be carried, and vice versa. Similarly, for a fixed bitrate level, the more efficient the audio codec is, the higher the audio quality will be. Error correction coding. Error correction coding is an important technology for a digital communications system because it determines how robust the reception will be for a given signal strength. Stronger ECC will provide more robust reception than a weaker form. The old version of DAB uses punctured convolutional coding for its ECC. The coding scheme uses unequal error protection, which means that parts of the audio bit stream that are more susceptible to errors causing audible disturbances are provided with more protection, and vice versa. However, the UEP scheme used on DAB results in there being a gray area in between the user experiencing good reception quality and no reception at all, as opposed to the situation with most other wireless digital communication systems that have a sharp digital cliff, where the signal rapidly becomes unusable if the signal strength drops below a certain threshold. When DAB listeners receive a signal in this intermediate strength area, they experience a burbling sound which interrupts the playback of the audio. The new DAB Plus standard has incorporated Reed-Solomon ECC as an inner layer of coding that is placed around the byte interleaved audio frame, but inside the outer layer of convolutional coding used by the older DAB system. Although on DAB Plus the convolutional coding uses equal error protection rather than UEP, since each bit is equally important in DAB Plus. This combination of Reed-Solomon coding as the inner layer of coding, followed by an outer layer of convolutional coding, so-called concatenated coding, became a popular ECC scheme in the 1990s, and NASA adopted it for its deep space missions. One slight difference between the concatenated coding used by the DAB Plus system and that used on most other systems is that it uses a rectangular byte interleaver rather than Forney interleaving in order to provide a greater interleaver depth, which increases the distance over which error bursts will be spread out in the bit stem, which in turn will allow the Reed-Solomon error decoder to correct a higher proportion of errors. The ECC used on DAB Plus is far stronger than is used on DAB, which, with all else being equal, would translate into people who currently experience reception difficulties on DAB receiving a much more robust signal with DAB Plus transmissions. It also has a far steeper digital cliff, and listening tests have shown that people prefer this when the signal strength is low compared to the shallower digital cliff on DAB. Modulation immunity to fading and intersymbol interference is achieved without equalization by means of the Ofdm and DQ-PSK modulation techniques. For details, see the Ofdm system comparison table. Using values for the most commonly used transmission mode on DAB, transmission mode I. The Ofdm modulation consists of 1,536 subcarriers that are transmitted in parallel. The useful part of the Ofdm symbol period is 1 millisecond, which results in the Ofdm subcarriers each having a bandwidth of 1 kHz due to the inverse relationship between these two parameters, and the overall Ofdm channel bandwidth is 1,537 kHz. The Ofdm guard interval for trademark I is 246 microseconds, which means that the overall Ofdm symbol duration is 1.246 milliseconds. The guard interval duration also determines the maximum separation between transmitters that are part of the same single frequency network, which is approximately 74 kilometers for trademark I. Single-frequency networks. Ofdm allows the use of single-frequency networks, which means that a network of transmitters can provide coverage to a large area up to the size of a country, where all transmitters use the same transmission frequency. Transmitters that are part of an SFN need to be very accurately synchronized with other transmitters in the network, which requires the transmitters to use very accurate clock box. When a receiver receives a signal that has been transmitted from the different transmitters that are part of an SFN, the signals from the different transmitters will typically have different delays, but to Ofdm they will appear to simply be different multipaths of the same signal. Reception difficulties can arise, however, when the relative delay of multipaths exceeds the Ofdm guard interval duration, and there are frequent reports of reception difficulties due to this issue when there is a lift, such as when there's high pressure, due to signals traveling farther than usual, and thus the signals are likely to arrive with a relative delay that is greater than the Ofdm guard interval. Low power gap filler transmitters can be added to an SFN as and when desired in order to improve reception quality. Although the way SFNs have been implemented in the UK up to now, they have tended to consist of higher power transmitters being installed at main transmitter sites in order to keep costs down. Bit rates. An ensemble has a maximum bit rate that can be carried, but this depends on which error protection level is used. However, all DAB multiplexes can carry a total of 864 capacity units. The number of capacity units or CU that of certain bitrate level requires depends on the amount of error correction added to the transmission, is described above. In the UK, most services transmit using protection level 3, which provides an average ECC code rate of approximately 1/2, equating to a maximum bitrate per multiplex of 1184 kbit per second. Services and ensembles. Various different services are embedded into one ensemble. These services can include primary services, like main radio stations; secondary services, like additional sports commentaries; data services, electronic program guide, collections of HTML pages and digital images, slideshows, which may be synchronized with audio broadcasts. For example, a police appeal could be broadcast with the e-fit of a suspect or CCTV footage. Video Java platform applications, IP tunneling, other raw data. DAB+. The term DAB most commonly refers both to a specific DAB standard using the MP2 audio codec, but can sometimes refer to a whole family of DAB-related standards, such as DAB+, DMB and DAB-IP. DAB+. WorldABA, the organization in charge of the DAB standards, announced DAB+, a major upgrade to the DAB standard in 2006, when the HEAACV2 audio codec was adopted. The new standard, which is called DAB+, has also adopted the MPEG surround audio format and stronger error correction coding in the form of Reed-Solomon coding. DAB+ has been standardized as European Telecommunications Standards Institute TS 100 2563. As DAB is not forward compatible with DAB+, older DAB receivers cannot receive DAB+ broadcasts. However, DAB receivers that will be able to receive the new DAB+ standard via a firmware upgrade went on sale in July 2007. If a receiver is DAB+ compatible, there will be a sign on the product packaging. DAB+ broadcasts have launched in several countries like Australia, Czech Republic, Denmark, Germany, Hong Kong, Italy, Malta, Norway, Poland, Switzerland, the United Kingdom and the Netherlands. Malta was the first country to launch DAB+ in Europe. Several other countries are also expected to launch DAB+ broadcasts over the next few years, such as Austria, Hungary, and Asian countries, such as Thailand, Vietnam and Indonesia. South Africa began a DAB+ technical pilot in November 2014 on Channel 13F in Band 3. If DAB+ stations launch in established DAB countries, they can transmit alongside existing DAB stations that use the older MPEG-1 audio Layer 2 audio format. and most existing DAB stations are expected to continue broadcasting until the vast majority of receivers support DAB+. Ofcom in the UK has published a consultation with the intention to set up a new multiplex containing a mix of DAB and DAB+ services, with the intention of moving services to this format in the long term. In February 2016, DAB+ stations launched in the UK as part of a new national network. DMB digital multimedia broadcasting and DAB IP are suitable for mobile radio and TV both because they support MPEG-4 AVC and WMV9 respectively as video codecs. However, a DMB video subchannel can easily be added to any DAB transmission, as it was designed to be carried on a DAB subchannel. DMB broadcasts in Korea carry conventional MPEG-1 Layer 2 DAB audio services alongside the DMB video services. Norway, South Korea and France are countries currently broadcasting DMB. Countries using DAB. More than 30 countries provide DAB, DAB+, and/or DMB broadcasts, either as a permanent technology or as test transmissions. DAB and AM/FM compared. Traditionally, radio programs were broadcast on different frequencies via AM and FM, and the radio had to be tuned into each frequency, as needed. This used up a comparatively large amount of spectrum for a relatively small number of stations, limiting listening choice. DAB is a digital radio broadcasting system that, through the application of multiplexing and compression, combines multiple audio streams onto a relatively narrow band centered on a single broadcast frequency called a DAB ensemble. Within an overall target bitrate for the DAB ensemble, individual stations can be allocated different bitrates. The number of channels within a DAB ensemble can be increased by lowering average bit rates but at the expense of the quality of streams. Error correction under the DAB standard makes the signal more robust but reduces the total bitrate available for streams. FM HD radio versus DAB. Some countries have implemented Eureka 147 digital audio broadcasting. DAB broadcasts a single station that is approximately 1,500 kHz wide. That station is then subdivided into multiple digital streams of between 9 and 12 programs. In contrast, FM HD radio shares its digital broadcast with the traditional 200 kHz wide channels, with capability of 300 kbit per second per station. The first generation DAB uses the MPEG-1 audio Layer 2 audio codec, which has less efficient compression than newer codecs. The typical bitrate for DAB programs is only 128 kbit per second, and as a result most radio stations on DAB have a lower sound quality than FM, prompting a number of complaints among the audiophile community. As with DAB+ at EDMB in Europe, FM HD radio uses a codec based upon the MPEG-4 AAC standard. HD radio is a proprietary system from the company Ubiquiti. DAB is an open standard deposited at ETSI. Use of frequency spectrum and transmitter sites. DAB gives substantially higher spectral efficiency, measured in programs per megahertz and per transmitter site, than analog communication. This has led to an increase in the number of stations available to listeners, especially outside of the major urban areas. Numerical example: analog FM requires 0.2 MHz per program. The frequency reuse factor in most countries is approximately 15, meaning that only 1 out of 15 transmitter sites can use the same channel frequency without problems with code channel interference, i.e. crosstalk. Assuming a total availability of 102 FM channels at a bandwidth of 0.2 MHz over the band 2 spectrum of 87.5 to 108.0 MHz, an average of 102 15/6.8 radio channels are possible on each transmitter site. This results in a system spectral efficiency of 1/15 equals 0.30 programs transmitter megahertz. DAB with 192 kbit per second codec requires 1.536 MHz asterisk 192 kbit per second 1136 kbit per second equals 0.26 MHz per audio program. The frequency reuse factor for local programs and multi-frequency broadcasting networks is typically 4 or 5, resulting in 1/4 equals 0.96 programs transmitter megahertz. This is 3.2 times as efficient as analog FM for local stations. For single-frequency network transmission, for example of national programs, the channel reuse factor is 1, resulting in 1/1. 0.25 MHz equals 3.85 programs transmitter megahertz, which is 12.7 times as efficient as FM for national and regional networks. Note the above capacity improvement may not always be achieved at the L-band frequencies, since these are more sensitive to obstacles than the FM band frequencies, and may cause shadow fading for hilly terrain and for indoor communication. The number of transmitter sites of the transmission power required for full coverage of a country may be rather high at these frequencies, to avoid the system becoming noise-limited rather than limited by code channel interference. Sound quality. The original objectives of converting to digital transmission were to enable higher fidelity, more stations and more resistance to noise, code channel interference and multipath than in analog FM radio. However, the leading countries in implementing DAB on stereo radio stations use compression to such a degree that it produces lower sound quality than that received from non-mobile FM broadcasts. This is because of the bitrate levels being too low for the MPEG Layer 2 audio codec to provide high-fidelity audio quality. The BBC Research and AMP Development Department states that at least 192 kbit per second is necessarily for a high-fidelity stereo broadcast. A value of 256 kbit per second has been judged to provide a high-quality stereo broadcast signal. However, a small reduction to 224 kbit per second is often adequate, and in some cases it may be possible to accept a further reduction to 192 kbit per second, especially if redundancy in the stereo signal is exploited by a process of joint stereo encoding. At 192 kbit per second, it is relatively easy to hear imperfections in critical audio material. When BBC in July 2006 reduced the bitrate of transmission of Radio 3 from 192 kbit per second to 160 kbit per second, the resulting degradation of audio quality prompted a number of complaints to the corporation. BBC later announced that, following this testing of new equipment, it would resume the previous practice of transmitting Radio 3 at 192 kbit per second whenever there were no other demands on bandwidth. Despite the above, a survey of DAB listeners has shown most find DAB to have equal or better sound quality than FM. Notwithstanding the above, BBC Radio 4 has extended the periods it broadcasts programs with a lower bitrate and in mono in 2012. such as the Today program, rather than 128 kbit per second, and in stereo. Programs which had traditionally been broadcast on BBC Radio 4 DAB in stereo can now only be heard in the evenings in mono, even though the same programs still go out in stereo in Radio 4 FM, digital TV and online. The BBC have issued a statement stating that stereo is still the default for BBC Radio 4 DAB. However, after the Olympics, this does not appear to be the case in the evenings, making FM broadcasts superior, as very few car radios are currently fitted with DAB if the BBC switch FM off as indicated later in the decade. Some listeners may be forced to receive mono broadcasts in the future, a somewhat backward step. An audio quality comparison of PCM, DAB, DAB+, FM and AM is available here.